So welcome to Stat 310 Lecture 6. A couple of announcements to begin with. Homework 1, hopefully you know by now, is due September 10th. That's a Thursday. And homework 2 is due September 17th. So for most weeks, you can expect that there'll be a homework due on Thursday that'll cover material in the lecture. And this is a good way to check that you're kind of following things and are on track in terms of your understanding. So today we're going to cover parts of chapter 7 of the textbook, which it focuses on survey sampling, and in particular we're going to look at properties of the sample mean and sample variance in this context. We talked a bit about that in the context of the independent normal sample earlier, which comes from chapter 6. In chapter 7, we're looking at the setting where we have where we have survey samples, which we introduced in the previous lecture, and we're going to go into more detail in today's lecture, or in this lecture. And in particular, there were two sampling schemes that we're going to compare and contrast: independent random sampling, which involves sampling with replacement, and simple random sampling, which involves sampling without replacement. And so we're going to look at the properties of sample mean and sample variance under those two different sampling schemes. So just to recall the setup for survey sampling. So in survey sampling, it's like you have a finite population of size big N, where big N is typically going to be pretty large. And then you draw N samples from that big population. So N is your sample size, little n, and so little n is going to be less than or equal to big N, often much smaller. And so a good example to just keep in mind, actually, once again goes back to the first lecture, and there's many other examples of survey sampling that arise, but you can think about voting in Wisconsin. So the entire population of Wisconsin, I believe, is about 6 million or maybe 5.8 million or something. It changes, but roughly I think it's 5.8 to 6 million. So we're just going to kind of say that it's approximately 6 million. And then in the sample that we draw, I mean, you can draw any number of samples, but in terms of getting a good survey sample, we discussed a sample size of n equals 100. So you can see that in this setting, your sample size is typically much smaller than your population size. But this is a good example to keep in the back of your mind. In general, when I'm introducing new concepts and notation, it's always good to have a specific example in the back of your mind, just to keep things concrete. So, as always, we're going to try to tie things back to our statistical framework, because that gives us kind of a firm grounding. We covered the statistical framework in the previous lecture. So our data here is our sample. So this is our sample. You typically you don't know what the entire population is. That's something you don't know, and you're trying to infer from the sample. The second component is the distribution of the sample data, and the population parameters. So we're going to first talk about that. We talked about this in the previous lecture, but we're going to kind of reinforce it here. So there's we know that we assumed that each person from the population, or each element of the population, is equally likely to be drawn. So the probability that xi is equal to we'll say psi j, so this is a psi or psi, is just 1 on n. So you're 1 on big N. So you're uniformly distributed across the population. And so what that means is that we can define the population parameters are, firstly, we can define the population mean, which is the expectation of xi, which is just the average of the c's, so taken over big N. I'm going to try to use the subscript j for the population for the population and I for the sample, just to distinguish and make sure the notation doesn't get too confusing. And then the other population parameter, which is the variance of these xi's, is given by this. So this is just using the formulas for how to calculate expectations and variances for a random variable. The next thing that I mentioned that's important is that there are two different sampling schemes that we talk about, and those are important because they're going to influence the distribution of the xi's and relative to each other. So the first one I talked about was independent random sampling. So it's sampling with replacement. And the reason it's called independent random sampling is that it means that x1, x2, that all of your samples are independent. The next notion of sampling, which is actually what's typically used in practice, is simple random sampling, and that's sampling without replacement. Okay, and so in this case, the xi's are not independent because you're essentially taking one person out of the population at each go. So this means that you're not going to have independence in this case. And we'll talk a little bit more, we'll go into a little bit more detail on IRS versus SRS through this lecture, and we'll talk about sort of why we consider both. The statistics we consider are the sample mean, so this only is a function of only the sample data, and then the sample variance. Okay, so to be clear, I've used this 1 over n minus 1 because that's the consistent definition that we've used, and I discussed why we actually used that in the previous lecture, because we want to make sure that the expectation of s squared equals sigma squared for our and that's why we have the n minus 1. The book uses 1 over n instead of 1 over n minus 1. If n is large, this like 100 or something, this is not going to make a big difference because it's n versus, it's on the denominator and it's n versus n minus 1. But I'm going to use n minus 1 to be consistent throughout this course. So in the textbook, if you see 1 over n, you don't have to worry too much about it. Throughout this course, the sample variance is always going to be defined with this 1 over little n minus 1. And so so the key question we're going to address today are, so what are properties of x bar and s squared under both IRS and SRS? So that's a key question we're going to look at today. So we're just going to talk intuitively and, if we think practically and intuitively about what's going on with IRS and SRS, just to kind of give us, some grounding. Like this will be useful before we dive into the math. So typically, as we will see, IRS is um, makes calculations a lot easier. Since we have independence. SRS, more widely used in practice. Used in practice. Because it's often impractical to replace samples. So I mentioned right at the beginning of this lecture the voting example. So think about the voting example. If you did IRS, that would basically mean that after you ask someone who they're going to vote for, you essentially put them back into the population, and then you potentially could ask them again. And that's a little bit weird, as you can imagine. So simple random sampling is what's typically used more in practice, because you often, once you survey someone or ask, access one of the samples or one of the elements of the population, it's often impractical to access that again. So that's why SRS is more widely used in practice. So in this course, though, we're going to focus more on IRS. That's after today. So for this week, for this lecture and possibly the next lecture, we're going to talk about IRS and SRS in a little bit of detail. But after that, we're going to focus more and more on independent sampling. And, you might ask the question, why? And it is largely because the calculations are a lot easier. And then the second reason why is that we'll also see this in the calculations today, is that if n is much larger than n, then IRS and SRS calculations very similar. So again, go back to the example. So So if we think the voting in Wisconsin example, we have that n's approximately 6 times 10 to the 6, and little n is approximately is 100 exactly, or however big we make the sample. On the one hand, what you typically do in practice is simple random sampling, because you would not ask, you generally, if you've asked someone who they voted for, sorry, you're generally not going to replace them in the sample and then, potentially ask them again. So that's why SRS is used more in practice. But on the other hand, if the population size is about 6 million or 5.8 million, and your sample size is 100, there's very little chance that you're going to ask the same person twice anyway. So the calculations you get from IRS and SRS are going to be very, very close. Excuse me, sorry. And we're going to see that in the calculations that we do. So we're going to first discuss independent random sampling, and we'll actually see that the calculations are pretty nice and pretty simple. And in that case, in SRS, we'll see that the math can get pretty, pretty curly pretty quickly. But we'll hopefully see that that particularly in the case where the population size big N is much bigger than the sample size little n, the difference between them isn't too much. So what can we say about x bar? So we know that we can do this calculation. So we've done this calculation many times before, but using linearity of expectation. Okay, and then we also have that, and so this and then if we wanted to calculate the variance of x bar, then we know that when we pull out a constant, it gets squared for variance, and so we end up with sigma squared over n. So this is where we use independence. And this is really the crux of why independent random sampling makes the calculation a lot easier. We'll see that calculation for simple random sampling is going to be a lot more difficult. And so we also know that by the central limit theorem that we know that thing converges to normal 0, 1. And this allows us to do calculations using standard normal if n is large. And when we say large here, we're talking about a different kind of large to big N. A size of n equals 100, a little n equals 100 is certainly large enough. So and as I mentioned, you can kind of go back and see the voting example. And we certainly use these calculations throughout. So how about s squared? So we know that so a natural question we can ask is like, what's the expectation of s squared in this case, and does it look anything like the population variance? So once again we can use linearity of expectation. And we're again see sort of why the n-1 comes out here. So we do this this trick of adding and subtracting the so this is something we saw in the previous lecture. And And so we end up with okay, because we get a factor of 2 here, and then we have 1 here, and so that leads to okay, and so this just we just add up the variance of the xi's, and then we subtract the variance of x bar basically, and then multiply by n. And so this gives us n sigma squared, and then we get n times sigma squared over n. And so this gives us exactly sigma squared. And again, that's where the n minus 1 comes from, because it means that the expectation of s squared equals sigma squared. And as I mentioned, if you replace the little n minus 1 with a little n, it's not going to make things too different, provided your little n is reasonably large. And a natural question to kind of think about here is why in the population do you have big N for the variance, for the population variance, but in the sample you have little n minus 1 instead of little n? And this is a very interesting question to think about, and and something that, intuitively might take a little bit of time to kind of grasp. So, and the reason at a high level is that the interpretation is that since sample mean x bar is random, you are using data to estimate population mean mu. And so this means you lose 1 degree of freedom. 1 degree of freedom. We're going to see degrees of freedom come up a lot later in the course when we talk about analysis of variance, but this is kind of one interpretation for why we have the n minus 1 here, because you can see that in the calculation that you kind of have to, because x bar depends on the data, and it's not kind of an exact fixed quantity. You have to add and subtract the mu, and the mu, the population, and that kind of makes you lose 1 degree of freedom because there's some variability due to the sample variance as well. To the sample mean, which you have to account for, and this is why you have the 1 over n minus 1 there. Okay, and if that doesn't make sense to you right now, that's okay. Another way you can just also interpret this is you need that to ensure that you need the 1 over n minus 1 just to ensure that the expectation of s squared is sigma squared. And this is important because we have that but the question is that if sigma is unknown, which is often the case in practice, you don't know the population variability typically, then you can also say that that's going to converge to normal 0, 1. So, and another way to think about that is that, you know, so that's going to converge to t n minus 1, which is going to converge to normal 0, 1 as n goes to infinity. So we saw that the t distribution kind of arises if you subtract off the mu. That's in the scenario where everything's normal and we could do the calculations exactly. But here, you know, if you divide by s, where the variance is unknown, then you're going to get that this converges to a t distribution, but then a t converges to a normal as n goes to infinity. And the other thing to note is that population size n, big N, plays no role and we'll see that that isn't going to be the case when we have simple random sampling. So the rest of this lecture, we're going to see some, you know, some more funky calculations that we have to deal with when we start looking at simple random sampling. So the sample data doesn't change here. And our statistics stay the same. So we have and again, in the textbook, I believe they use a 1 over n, but we're going to use a 1 over n minus 1 throughout the course. That, like, often you'll see different conventions in different places, but we're going to stick with 1 over little n minus 1 in this course. Okay, and so the challenge here is that the xi's are not independent, but the xi's have the same distribution. And the other thing that's nice is, and the way you can kind of see that is that even though you're drawing without replacement, if you imagine that, you know, if you look at the fourth element that you draw compared to the first element that you draw, because you didn't, like, if you look at just the fourth draw and don't think about the others, you don't really, like, you have no information about the first 3 draws for your fourth draw, which means that the distribution of that fourth draw, if you don't think about the others, is just going to be the same. So that's why the xi's will have the same distribution. And the other thing that's important is that xi, xk, for I not equal to k, they have the same joint distribution. And we're going to use both of these properties in our calculations, but we can't use independence anymore because our samples are not independent. And so once again, the reason for that is so for example, if you think about, say, x2, x3, which is kind of the second draw and the third draw, versus, say, x like 7, x like 15, for example, the reason why they have the same distribution is the same logic as to why each individual random variable has the same distribution. Because if you look at just the second and third draws kind of as just 2 draws, and you don't worry about what happened on the other draws, which is what the joint distribution looks at, that's going to essentially be the same as if you looked at the 7th and 15th draw, because you have no information about what happened on any of the other draws. And so you can think about that in the context of kind of drawing cards from a deck. the distribution of the joint distribution of any pair of cards that you draw is going to be the same, regardless of which pair that is. So the first thing is, what can we say about x bar? So the calculation of E of x bar isn't going to change because we didn't really use any independence there. All we used was the linearity of expectation, and I mean that is true regardless of independence. And so we're still going to get mu because we're just relying on linearity of expectation here. Now we'll see that the variance of x bar that's going to be a more challenging scenario because we don't have independence anymore. So what we would typically do, as we do in the independence case, is that, or we do in the independent random sampling case, is that you just you can take out the 1 over n squared as we did before. And then we can take the variance of the sum. But what we can't do now is we can't pull, since we're not independent anymore, we cannot bring the variance inside. Okay, and we'll see that that's going to make our life a little bit difficult, but we'll still be able to proceed, and we'll see how. And if anything's not kind of making sense right here in terms of why are things not independent in the SRS case versus the IRS case, and why are the joints the same distribution just as the individual random variables are. So one example to think about is so think about drawing 5 cards from a 52 card deck with and without replacement, and then think about things like, x1 through to x5, independences and so on. Okay, so now let's return to this calculation. Okay, so we can't bring the variance inside, but another very useful way of dealing with variance that you hopefully saw in 309, and we've already seen once or twice here, is that you can use this notion of covariance, and the variance of 2 random variables is the covariance of the random variable with itself. And covariance is a bilinear operator, and so you can always just bring the covariance inside here. So you can write this out like this. Okay. And now we can, do something pretty, this is where we're going to exploit the properties that the xi's have the same distribution, and the joints also do as well, because we have to now worry about the joint distribution of xi and xk, because we're calculating covariances here. And so what we can say here is we can split this up into 2 scenarios where I equals k, and then we can split it up into the second scenario where I is not equal to k. Okay, so there are clearly going to be n terms here, and then n times n minus 1 terms for the second part. Okay, so we know that the covariance of something with itself is just the variance of xi. And then we also know that we can rewrite this because we know that everything's identically distributed. We can just rewrite this as the covariance of x1 and x2, because since we know that the joints are all the same, we know that the covariance of x1, x2 is just going to be the covariance of xi, xk for all k not equal to I. Okay, and so this is going to make our calculation a lot easier, but still not super easy, as we'll see. So we can write this as n times sigma squared, which is the variance of these xi's, plus n times n minus 1 times the covariance of x1, x2. Okay, so now, so we've gotten to this point in the calculation, and so the next thing to do is we need to find the covariance of x1, x2. And here we're going to use a lot of knowledge from 309, and some of this I covered in the revision, but some of this I didn't. But it's something that, if you do get stuck, it's something you can look back at. This kind of calculation is not one we're going to see a lot throughout the course. So if you don't, if it doesn't come very naturally to you, it's okay. But it's something that you'll certainly need for this week's homework, and so it's useful to follow. And particularly if you want to kind of get a good understanding, it's useful to just get an idea of how these steps follow. So you should be able to follow these steps, but you're unlikely to have to reproduce them in a midterm or a final. So to find covariance of x1, x2, one of the definitions that we have is that this is just, or an expression for it is expectation of x1, x2 minus expectation of x1 times expectation of x2, right? So we know that the expectation of x1 and the expectation of x2 is just mu, and so we have mu squared here. And so so we need to find the expectation of x1 times x2. And so here we go back to the definition. So we have discrete random variables here because the population, so this is going to be a calculation in the population because x1 and x2 are drawn from this population. And so the x1 and x2 can take on big N different values. And so this is going to be probability x1 equals so this is the definition of the expectation of x1, x2. We're just using the definition of the expectation of two random variables when you have the expectation of two random variables. So it's the joint distribution times those values, and then you sum them up over the different possibilities. So if things were independent, it would be a lot easier because you could just split up the probability, but you can't because they're not. But what we can do, and what we hopefully remember somewhere in the back of our mind from 309, is that you can rewrite this as the conditional probability. And then times, again, we're just using the fact that the joint distribution is just the product of the conditional, or you can think about this as, probability A intersect B is probability A times probability of B given A. And now, we know that the probability x1 equals Cj is just 1 over n. You're just drawing these at random. And then the probability that x2 equals Cl, so you've removed one of the samples, and there's just the other one, like the other n minus 1 left. So this is going to be 1 over n minus 1. But we have to remember that if L happens to equal J, then you can't possibly draw that again. So this, I'm going to also have to have this indicator here that L is not equal to J, and then times that by CJ and CL. Okay, and so just to remember that indicator of L not equal to J, that just equals to 1 if L is not equal to J, and 0 if L equals to J. And that just makes sure that you can't draw the same sample twice. Okay, so we can now take out the n times n minus 1 here. CL times CJ. And so what we can do now is we can now only subtract over so we end up with this subtraction where we only subtract over L not equal to J, CL, CJ. But that's quite hard to calculate, so it's a lot easier to actually subtract over everything. So we're going to subtract over everything, and then like we're going to subtract the scenario where they're the same. So this is CJ squared. So I've just expanded things out because we can write this in terms of the population parameters in a much more straightforward way. Okay, and so and we can now split that sum up. And you're just going to get n squared mu squared. And then we also notice here that this is just exactly equal to minus n times it's sigma squared plus mu squared. And the reason why that's the case is that sigma j squared, that just equals to the expectation of xi squared, right? Just by definition. And so that's just going to equal to sigma squared plus mu squared. And then we don't have the 1 over n there, which is why we get n times sigma squared minus mu squared. And so what we end up with when we complete this calculation is just n times n minus 1 mu squared, and then minus n sigma squared. So therefore we have that this thing's going to be equal to mu squared minus 1 over n minus 1 sigma squared. So therefore the covariance of x1, x2, which is equal to e of x1, x2 minus mu squared. That's just going to be equal to negative 1 over n minus 1 sigma squared. Okay. So remember that if things are independent, this covariance would be 0. But you can see there's a little bit of dependence that we incur because we have a finite population. So you can see that as n gets bigger, this number gets smaller. And that kind of makes sense that, if your population is so big, then the dependence between the draws is going to get less as well. So now let's, I know this is a lot to keep track of. Let's return to our original equation here, which just says that so let me just remind us of that. It's okay, so we end up with a variance here equals to, there's two ways we can think about this, 1 minus little n, or we can rewrite this as big N minus n over big N minus 1. And we can recall that in the IRS case, variance of x bar equals sigma squared over n. So and then in the SRS case, variance of x bar equals sigma squared over n times and so or so this is the correction factor. Correction factor, little n minus 1 over big N minus 1. And then, as I mentioned before, note that if big N is much, much bigger than little n, n minus 1 over n minus 1 close to 0. And SRS and IRS calculations, they're going to be very close. So, so just to, again, sort of go back to the concrete example of voting in Wisconsin. If we consider voting in Wisconsin, remember that we had like N was 100 and N was about 6 million. So in that case, you can see that N minus 1 over big N minus 1 is going to be approximately, it's going to be like about 10 squared divided by 6 times 10 to the 6, which is going to be about 1.7 times 10 to the power of negative 5. And so therefore difference is very small. And so what we can say then is, therefore, even though we have an SRS scenario in practice, if we use calculations for IRS, approximation is very, very close. So, and that's why, I mean, if you go back to the first lecture, we did the calculation as though the samples were independent, and even though, like, in practice, as I mentioned, you typically, like, if you ask someone their vote, you're not going to ask them again, or you're not going to replace the samples and then draw another sample independently. But the numbers are going to be so close because your population's about 6 million and your sample size is about 100. So really, if you did the calculation for SRS, you could see that that's a lot more of work, and you don't really gain very much in terms of the results that you get. It's a little more accurate, but the difference is so small that you're not going to kind of notice a big practical difference. Finally, we'll finish with what we can say about S squared, and this calculation's not quite as bad because we've done a lot of the hard work by calculating the variance of x bar. So remember that S squared here is 1 over n minus 1, and this is obviously for the SRS case. And once again, I'm using this with the little n minus 1 to be consistent. And so we can again kind of expand things out as we did before. So I'm just kind of repeating the calculation that I did earlier. I'm skipping a few steps because we can go straight to this expression. So typically you would add and subtract the mu and expand out the square. And then the cross term would give you a factor of 2, and the additional quadratic term would give you a factor of 1, which cancels out to be this. I would say, sorry, I should put the expectation here, sorry. Let me just erase this and, ooh. Sorry, this is just doing the expansion without thinking about expectation at all. And so if you're confused by how to do this, I would encourage you to do this exercise. This is going to be a useful exercise throughout the course because we're going to see these types of little calculations come up in the homework a lot. And so we can see that we can once again see that we get that this is going to be n times the variance of variance of xi, or x1, we'll say, minus n times the variance of, sorry, there's no, so n times, you're right, yeah, that is correct. So n times the variance of x bar. Okay, and so we know that this is going to be 1 over n minus 1, and then n times sigma squared. And then we're going to subtract off n, and then we have sigma squared over n times n minus. So this is using the formula we already had from the variance of x bar. So that tedious calculation we did earlier. And so what we end up with here is okay, and if you expand that out, you get So we're going to get n minus 1 for the sigma squared times n, and then divide that by n minus 1. Because we're going to get the sigma squared n terms will cancel out. And so we end up very conveniently with just big N over big N minus 1 sigma squared. So we can once again see that as n gets large, okay, and I no, I think that so to finish off this lecture, I'll just sort of make a few comments about why we did this and what we're going to do in the future. So the purpose of seeing this SRS versus IRS calculation is use simple random sampling for surveys. But in theory, we do calculations assuming IRS. So as I mentioned before, in practice, you typically, once you draw a sample, you can't really replace it, put it back, and then draw another sample. So we can see that in practice you typically use SRS, and then as we saw earlier today with the calculation of the variance of X bar, and it can get a lot more complicated if you look at things like the variance of S squared and so on. The calculation becomes very tedious once you start doing SRS, and so for the calculations we typically do IRS. That's what we did in the first lecture. I kind of just so that they're independently drawn Bernoulli, even though in practice, you typically wouldn't sample with replacement. And so we can see that if n is much less than n, IRS is a good approximation to SRS. Approximation to SRS, but obviously if you're in a scenario where big N is like, say, 50, and then you draw like 20 or 50 samples, then you can see that but if N is comparable to N, if little n is comparable to big N, IRS is not a good approximation to SRS. Okay, because remember that we have the that like big N minus little n term in the numerator. So clearly, if they're the same, you're just going to get a very different result. And for the remainder of the course, we're going to mainly focus on IRS because, as you saw, how much more difficult the calculations become once you don't assume independence, and that they, in most settings in practice, you're going to have enough size in the population that it's not going to really matter. So So we're typically going to use independent sampling or independent random sampling for the remainder of the course. Okay, so thanks very much. That'll be everything for this lecture.